Okay, we'll begin our lesson, everybody. Zooming out a bit, there we go. So today, what we'll begin our revision with is a test summary. So I'm going to talk about the skills that are present, we'll talk about the conditions of the test, and then we will go through a review together. And following that, you've got some DIY revision. So this will probably take us pretty close to recess. And then after recess, it's all up to you where you're going to dedicate your time. So it's going to be a fat test, it's going to be a challenging test, and we've got about a week to prepare, so it's a week from now, isn't it? Let's just have a summary of the content. So in exercise 3A, we did tangents and normals. Now, if you were looking at the textbook questions closely, they were only about tangents. Okay, so you are expected to know normals. It's a bit of a shortcoming of the textbook, but we've got some supplementary resources in the OneDrive that are specifically about normals. You'll see them pop up in the conjecture question booklet and so forth, but they're very similar to the equation of a tangent. Okay, so that's 3A. In 3B, we look at increasing and decreasing functions, so we're stating domains when a function is increasing and decreasing, and that we can observe just from looking at the graph, right? 3C, we did stationary points. So this is when the slope is not increasing and not decreasing, it's horizontal. And specifically looking at local maximum, local minimums, and stationary points of inflection. And then in 3D, we got into what the second derivative means, the sign diagram of the second derivative. If the sign diagram of the second derivative is negative, it's concave down. If it's positive, it's concave up. Point of inflection is occurring when the second derivative equals 0 and the sign diagram changes sign. And so yeah, point of inflection, special case known as stationary. Now all of 3B, 3C and 3D, I would expect we can observe all of those features on a graph. We're comfortable looking at a graph going, yep, here it's increasing, here it's decreasing, here's a max, here's a min, here's the points of inflection, here's concave up, here's concave down. So I expect us to be able to see all that from the graph. So you can see those features, but what we're doing is using calculus techniques to describe exactly where they're occurring. In 3E, we looked at kinematics, and I've just got a summary there of all the key points from kinematics. 3F, we did rates of change, which was a pretty straightforward one. And then 3G, optimization, fairly challenging exercise that we went through yesterday. So you can expect in this test, you can expect there's going to be a conjecture question, there's going to be a graphing question, there's going to be a question about tangents or normals, there will be one about optimization. And you'll observe those patterns in the practice test, okay? No questions are the same, but it does follow the same structure, a bit like the first test on differential calculus. So the practice tests are indicative of what kinds of questions we ask in the test. Okay, and then that really important table at the bottom, which helps you with those graphing questions, definitely expecting one of those. So our test will be on Friday the 11th of April over lesson 3 and 4, so 168 hours from now. We'll begin at 10:40. It goes for 70 minutes. So that's our plan at this stage. We'll begin like we did last time. We'll see if anyone has any questions, and if we're happy to get started, we'll just get started. You are permitted your graphics calculator. You get one single-sided A4 page of handwritten notes. We've given you the SACE formula sheet. You can bring that if you want it, and the unit circle I've given you, you can bring that if you want it as well. There's a summary of the content. And here's a bit of a skills checklist. So this skills checklist you can sort of scroll through. Do I remember how to do that? Do I know how to do that? Because those are the kinds of questions that we can expect in the test. If you're not sure what any of those checkpoints mean, maybe ask, but that would be, if you can tick off all of those, you should be pretty sorted for the test. Summary of revision resources. So we've got the tests 2017 through to 2024. They're printed at the moment, so most people are having all of them. Some people are only having the later 4. I'm very happy to print more if you need. The review sets, I've got all questions are relevant except 2. We've isolated 2 that aren't relevant. We've got the conjecture questions booklet. Okay, one of those conjecture questions will appear in the test. We've got the graphing relationships booklet. It won't necessarily be one of those questions, but definitely that skill, and we can provide more resources if you need. Okay, so with that in mind, let's get into the review here together. I would recommend doing this on some just graph paper, maybe in your book or at the back of your book. We're going to go through it together. Now, every test, what I would do is we would go through this together. You might remember from our first test, I set it as homework. Okay, I set it because we filmed it. I filmed it last year, and I said go watch it for homework and complete it for homework. We're going to go through it together now. There's one thing that's a little bit different this year that I just want to point out. But other than that, we'll go through it together. You can ask questions as we're going, and then the revision's up to you. So what we're doing here is what I call a comprehensive review. We're reviewing all of the skills together at the same time. So we have question 1. Find the equation of the tangent and normal to the function y equals e to the 0.5x at x equals ln4 in exact form. Okay, so for question 1, for a tangent and a normal, we need two things. We need the point of contact and we need the slope. Now we have the x value of the point of contact. We need the y value. Well, y is equal to e to the 0.5x. And so we're going to put in ln4 into that equation. So we have e to the 0.5 times ln4. And we can't simplify that straight away. You could, if you typed it in your calculator, it would pop out nicely. But what's going on here is we have a ln b. So we can take that number to be a power. So I'm going to do it nice and slowly. It's e ln 4 to the power of 0.5. Now 4 to the power of 0.5, that's 4 to the half. That means the square root of 4. So this becomes e to the ln 2, and e to the ln 2 simplifies to 2. All right. So we have ln 4, and the x and the y value is 2. We have our point of contact. All right. Next, we need the slope. So in order to find the slope, we need the slope function. So we're just going to differentiate our original function, 0.5 e to the 0.5x. All right, and we want to know the slope when x is ln 4. Now, I know that this part, 0.5 ln 4, I already know that that part simplifies to 2, right? We did it over here. So it becomes 0.5 times 2, which is 1. We have a slope of 1. All right, might be going a bit quick. Okay, so then we're finding the equation of a line, right, with these properties. Passes through that point, has this slope. So we'll start just with the tangent. Okay, so for the tangent, we would have y equals mx plus c. M is positive 1, so we have y equals x plus c, and it passes through this point. The y value is 2, the x value is ln 4. We can solve for c. See what I mean? And so therefore the equation of the tangent in exact form, y equals x plus 2, take ln 4. So just to draw this out, what's going on there? We solve for c, y equals mx plus c, so we're just chucking that c value there. There's the equation of the tangent. Now remember as well, we showed you how we can sketch the tangent from the graph. Okay, so if you graph the function, you can press F1 for sketch, and there's an option there for tangent and normal, and you can determine the x value where you want your graph to sketch it. So that's a way that you can backtrack and check your answer. Basically, for every skill, there's a way you can use your calculator to check your answer. All right, that's the tangent. Let's do the normal. Okay, so for the normal, we need the negative reciprocal slope. So the tangent has a slope of 1, so that means the slope of the normal is going to be minus 1 on top of 1. Okay, what we do is we flip it and we multiply it by negative 1. So at the moment, the slope is 1 on 1, we flip it stays as 1 on 1, but it becomes negative. So the normal has a slope of, we'll simplify to minus 1. So we'd have y equals minus x plus c. We put the 2 where the y is, and the minus the x value is ln4. And we solve for c, and then we'll state the equation of the normal. Alright, so what we have here, what we can sort of reveal is we have the y-intercept in exact form. When it says exact form, that means you can't round it, you can't use your calculator to evaluate it. It wants, like, m is -1, and the y-intercept of this line is 2 ln4. Okay, 2 plus ln4. Alright, any questions about question 1? Very good. So you can expect a tangent or normal question. You look at the practice test, you'll see that's the very first question on the page. We want to make sure we get all of those marks. Remember, in a test, there's easy marks and there's hard marks. Make sure you get the easy marks. All right, question 2. Consider the function x to the 3. f of x is x to the 3 times x take 2 squared. All right, find f dash of x and draw its sign diagram. All right, so here we have a couple of options. We could use the product rule, or we could expand it out to solve it. I'm in a bit of two minds. I think we will expand it. So this term here, what we have in front is x to the 3, and we'll just perfect square that one. We'll have x squared take 4x plus 4. And then we'll distribute the x to the 3. So we'll have x to the 5, 4x to the 4, and 4x to the 3. That's our derivative function. That's our original function, sorry. All right, so part A says differentiate and draw its sign diagram. Okay, so if we're going to differentiate, we're just using the power rule here. We get 5x to the 4, take 16x to the 3, plus 12x squared. Okay, that's the derivative function. And we're asked to draw a sign diagram. Now we could fiddle around with this and factorize it, okay? Like you can see x squared is common. X squared is the only thing that's common. We can pull that out the front, and then we have a monic quadratic, non-monic quadratic function. We could fiddle around with it, but we don't get marks for doing that. We're just asked to find f dash of x and draw its sign diagram. So what I'm going to do for this question, and you can anticipate, if you look again at the practice test, question 2 in the practice test will be like this, where you're given a function and we're going to differentiate it, and we're going to talk about features from what the derivative tells us, and then we're going to do the second derivative and talk about what those features tell us as well. So let's give it a graph. We're going to graph the original function. And the other thing to look out for is if we want you to sketch it and give you a Cartesian plane, and if we give you a Cartesian plane, the constraints, so the V window is on that Cartesian plane there. All right, so we're just sketching the original function, and I'm even just typing it in the way that they've given it to us. So typing it in like this. And what that does is it means if I've made a mistake in my expansion here, all right, unlikely, but if I've made a mistake in the expansion, and that's not quite right, it means I can still get the right graph of the derivative. So I'm sketching the original function as they've given it to us, and I'm going to use my calculator to sketch the graph of the derivative. Okay, so we remember how to do that. I'm going to turn the original function off and just focus on the derivative. We'll just start with a standard V window and then adjust accordingly. Standard V window is pretty good. All right, it's showing those roots. And so what we can see for our derivative function, its sign diagram is like this. We'll g-solve its roots. And we know x squared is a factor, so x squared is going to be a root. And then we have some irrational roots. Oh, no, 1.2 and 2. Nice. And it goes from above to below to above. Okay, so can everyone see that on their graph? I'll pause and make sure everyone can see it okay. All right, so you can expect this kind of question for question 2, right? It's going to say, sketch, find f dash of x, draw its sign diagram, and then, hence, when is it increasing? When is it decreasing? All right, so we're going to say it's increasing when the first derivative is positive, right? So we'll have when x is less than 0, when 0 is less than x is less than 1.2, and when x is larger than 2. That's when the first derivative is positive, so that means that's when the original function is increasing and decreasing. Okay, so we're not looking at the derivative function and seeing when does that have positive slope, when does it have negative slope. We're using this to make comments about the original function. And then it's decreasing between 1.2 to 2. Now, any questions about that so far? So what we're doing at the moment is covering 3b, increasing, decreasing. Then if we look, hence state the nature and coordinates of any stationary points. So now we're moving into 3c. All right, well, stationary points, we can see we have a local maximum at 1.2 because we're going from increasing to decreasing. We have a local minimum at 2 because we're decreasing to increasing. All right, so we'll list those out. We have a local max at x is 1.2. We have a local min at x is 2. We also have, what's going on here? We're increasing, it goes horizontal, and then it keeps increasing, stationary point of inflection. All right, so that's a stationary point. It's not a turning point, but it is a stationary point, and we're asked to find all of the stationary points and their nature. So we have a stationary point of inflection at x is 0. All right. And then the corresponding y values. Well, on the original function, I can already anticipate this y value will be 0, but the others we can g-solve a bit later. So we're going to remember to come back and fill those in. I'm just about, using your time most effectively, because we're looking at the derivative function at the moment. Okay, any questions so far? So look, you'll get, these are the easy marks, right? Look at that, simple differentiation, sine diagram, 2 marks, 2 marks, another 2 marks there, 3 marks there. There's 3 in this circumstance, but those are the easy marks to get. This question, we should be getting all these marks so far. All right, find f dash dash of x and draw its sine diagram. So now we're on to the second derivative, and if you've differentiated this using the product rule, all right, you're going to get another product rule and maybe 2 of them to do as well. So that's why this is going to be a little bit easier. So we can just go straight to here. We'll have 20x to the 3. And 3 times 16, what's that? 32, 50, 32, 48. X to the 2 and 24x. Okay, so that's our second derivative. And for its sine diagram, we'll just refer straight to our calculator again. All right, we'll turn the first derivative off. Option, calc. Second derivative. Draw the second derivative of the original function for me. Sketched it in green. G-solve those roots, and we've got 0. Well, we know that it's going to be 0 because that's a stationary point of inflection. We've got 0.710, and we've got 1.689. So we're round to 1.69. Okay, so that's f dash of x, and then we want when's it positive, when's it negative. So we're going from below to above, to below to above. Excellent. Okay. Hence, state the intervals where the function is concave up and concave down. Well, it's concave up when the second derivative sine diagram is positive. So concave up means between 0 and 0.71 and larger than 1.69. Concave down, value is less than 0. Now, just in terms of old notation, all right, what used to say, concave down was called just concave, and concave up was called convex. So that's some old notation. You might see that pop up in some of those old graphing questions. All right, hence, we will use explicitly concave up, concave down. Hence, state the nature and coordinates of any points of inflection. Well, we've already said there's non-stationary point of inflection at 0. And we know the corresponding y value. And then there's a stationary, sorry. That's a stationary point of inflection. These two are non-stationary. So we have one at 0.71 and the other at 1.69. And these are stationary points because the sign diagram of the second derivative changes sign. It goes from positive to negative and from negative to positive. So that means that has to be a point of inflection on the original function. Okay, so we've done part E, we've done part F, and then we have part G is a graphing question. You'll be given a Cartesian plane. I've spoken about how we allocate marks for a graphing question. So you've got to illustrate all of the features on the graph correctly. So let's sketch the original function and have a look at it and observe all of those features. So we'll talk about the features that we're going to want to see. So what we can see is it's concave down for values less than 0, and then here it changes to, it goes concave up, and then there's local max, and then it comes back down, and then it's concave. And then what we can do, now that we've sketched the original function, now just in terms of how we do allocate marks, right? All of these features, there's going to be a particular area where we want these features to occur. So we've got a grid that gives you a little bit of room for error, but if you've got the scale there, you G-solve those features and you observe where they occur and you just match them. Okay? So we're going to be identifying how you graph those features properly in the right position. All you're doing is copying it. All right, so make sure you get it right. Use trace to help you. Let's G-solve these coordinates that we haven't quite got yet. So I want to know when x is 1.2, what's the y value? 1.106. So that's going to be 1.11. When x is 2, what's the y value? 0. When x is 0.71. So I'm just typing these in. I'm getting all of them at the same time. Saves us a fair bit of time. That's going to be 0.5955. So 0.595. 6, sorry. And then when x is 1.69, and we've got 0.464. Okay. All right, so I've gone through, solved those. We've got the graph. We need to, our axes should be labelled if we're given a Cartesian plane, but we also need to label the graph. So we graph the original function, x to the 3 times x take 2 squared. And that's going to ensure that we get all of the marks. All right. And we can see all these features, right? When it's concave down, when it's concave up, there's the points of inflection here and here and here. Concave up, concave down, concave up. When it's increasing and when it's decreasing. Okay, any questions about that one? So definitely expect one of these questions. They're littered throughout the practice test and they're easy marks. I want us all to get them. Especially in the challenging test, we have to get all the easy marks. Okay, let's move on to the kinematics question. And we have the displacement of a footy above ground level is given by this equation. And we have 1 plus 15t take 4.9 t squared, where 0 is less than t is less than 3.1265. Okay, what I want to emphasize is that if we are given a constraint for a model, then we must operate inside that constraint. Now that means if we have to graph it, we don't graph it beyond that constraint. We have to answer questions about its domain. We don't answer beyond that constraint. So that'll pop up in this question. Find the velocity and acceleration functions and draw their sign diagram. Okay, so velocity is the derivative of displacement, so we'll just differentiate this. And then acceleration is the derivative of velocity, so we'll differentiate that. All right, we only consider positive values of time, and we're sketching from 0 to 3.1265. Okay, because we have those constraints, even our sign diagram is restricted. So we have from 0 to 0.31265. This function is just a negative horizontal line. You can check on your graph. This is the equation of a line with negative slope. We'll find out its root in a moment. 15 on 9.8. And it goes from above to below. Okay, 15 divided by 9.8. Just do it quickly in my head. 1.531. 1.53. All right, and make sure those are labelled clearly. This is V of t and this is A of t. Okay, good. Determine when the speed of the ball is increasing. Okay, so this is a fairly common type of question. So if we flick even just here, it's listed here, speed of an object, so under kinematics in the topic summary. Speed of an object, this is the bottom point. Speed of an object is the magnitude of its velocity. If V of t and A of t have the same sign, then the speed is increasing. If they have opposite signs, speed is decreasing. Now these two sign diagrams have the same sign between, so to answer part B, we're not going to say for values of t larger than 1.53. Why? Because the model is restricted over this parameter, this constraint. So we're going to have between 1.53 and 3.1265. Okay, so that's part B. Part C, what is the maximum height and when does it occur? Well, look at this sign diagram, right? This represents the velocity. And so if you think a footy's kicked into the air, when it reaches its peak, its velocity changes because it goes from increasing height to decreasing height. So it occurs when time is 1.53. So max height when time is 1.53. And so we just want to know, well, what's the displacement when time is 1.53? So we'll just evaluate that. I wouldn't bother graphing it because we just have one calculation to do, just in one number. Again, easy marks, and make sure you process the calculation correctly. Now I've got 12.47. Okay, so to three significant figures, 12.5. And our unit is meters, so make sure we use our units as well. All right, I reckon we can get 4 done. Okay, we have a question about a rave. So, any questions so far? Anyone want to have a quick breather? No? The number of people at a rave is given by the equation 10 ET cos t, where t is time in days after the rave starts. T is time in days. That might be an error on my part. T is time in days. Might be hours. We'll check. How many people are at the rave? Answer to the nearest integer. Part I initially. So the number of people at the rave is given by this equation, 10 e to the t cos of t. And we want to know how many people are there initially, how many people after 12 hours. Here's what we'll do. Let's sketch the function, and we're going to use that to answer parts A and B. The reason I'm sketching the function, like this is where it pays to read ahead, right? We're asked to calculate n of 0 and n of 12, and then 4.5. Let me sketch the function and see. I think I might have made an error when I said things there. So 10 ET cos t. And just, yep, definitely between 0 and make sure your calculator's in the radians. Yep, that's good. 10 e to the x cos x. okay, sorry, no, it is in days. So what that means, we'll just go sketch it from 0 to 1 for x, and for y, if we have from 0 to 10, it's not high enough. So let's go 30. And maybe we have to stretch x out a bit. I'm just adjusting it, right? So what I've sketched it over to get this kind of shape, I'm just fiddling around with it, and you'll have to do the same unless you're given a graph mode. I've sketched it between 0 and 2, and for y, I've got between 0 and 30. Okay, that's good. This is a surge function, I think. Type of surge function. It's period, sorry. So, how many people are at the rave? Answer initially. So we can put the number 0 in here if you want, but with the calculator we can solve these easily. We can just do n of 0, and so when we put 0 in here, that's going to be 1, that's 1, so that's going to be 10. But you can trace along, right? When x is 0, the y value is 10, and then we want after 12 hours. Now, we're told time is in days, so 12 hours is half a day. So that means we're finding n of 0.5. Okay, so I was right about the unit when I wrote it down. N of 0.5 is 12 hours is half a day. And this is 14.46. All right, now we're told round to the nearest integer. That means the nearest whole number. So this is closest to 14. All right, so we have n of 0 and n of 0.5. Then find n dash of t. In order to differentiate this function, we're going to need to use the product rule. We have u and v. One function multiplied by another. Smash them together. And this is n dash of t. It's the rate at which the number of people is changing. Okay. Then it says, determine the rate of change. Determine the rate of change, answer to 3 significant figures, initially. So when time is 0. So we're going back to when x is 0, and we're going, well, what is n dash of 0? So this is for part C, part 1, n dash of 0. Initially, the rate of change is, we've got the dy and dx is 10, straight from our calculator, and then after 12 hours, so 12 hours is half a day. Now there will be implied conversions, right, between 12 hours and half a day. Here, pop up in the practice test, maybe in the test. So after 12 hours, n of 0.5, I've got 6.564. Okay, now it says to 3 significant figures, so that's going to be 6.56. Now I suppose technically to 3 significant figures it's 10.0. On the front of your test it says 3 significant figures unless appropriate. So that's, we've given a bit of wiggle room there, where 10, like it's more appropriate to write that as 10 than it is 10.0, right? So we're just being realistic about it. Okay, we'll just finish this question and we'll break for recess, because we're pretty close to the end. So that's part D. E, when is the rate of change maximised? So all we can do there, all right, we're asked, when is the rate of change maximised? So what we should do is sketch the derivative function and g-solve its max. Now, if we've tried to do that, if we've graphed the rate of change function, what we see is it looks like this. Okay, and you press g-solve max and it's not popping out with the solution within our sort of constraints here, which means when is the rate of change at its highest value? Well, here. This is where it's furthest away from the x-axis. So the rate of change is maximised when time is 0. Now, if you're given a context, like sometimes you're given a context like the rave started at 12 AM or 12 PM or something like that, you answer in terms of the context of the problem. Okay, determine the exact value of t such that n dash of t equals 0. So we're asked, when does this function equal 0? Determine the exact value of t. So there's going to be a little bit of stuff from the first test here. This is where you've seen this kind of equation before. We want the exact value of t that satisfies this. So what we should do straight away is try and factorise whatever we can and apply that null factor. So we can see 10 e to the t is common. We're left with cos t takes sin t. E to the t does not equal 0, so that means this component has to equal 0. And so what it is, I think the best way to do it is to look at your unit circle and go, well, what are the values of t that make the cos value equal to the y sine value? So when is the x value equal to the y value? So on your unit circle, it's going to be here when they're both 1 on root 2, and here when they're both negative 1 on root 2. And so those values of t are going to be pi on 4 and 3 pi on 5 pi on 4. However, one of them's rejected because when time is 5 pi on 4, like if you keep sketching this function, this is what it does. It does something like this. Okay, so here's the pi on 4, here's the 3 pi on 4, and that's occurring, that's saying that we've had a negative amount of people in the rave, but you can't have a negative. So obviously the function is restricted to this domain, so this is our solution, pi on 4. So we'll reject that one. When t is pi on 4, we can round that to a few significant figures, like 0.789 or something. So if I go pi divided by 4, 0.785 days. So after 0.785 days, the rate of change, it's not increasing, it's not decreasing, the rate of change is 0. And that's all we're asked to do for part F. All right, so all we're drawing out in part F is just how to solve that kind of equation, because last year that popped up in one of the questions in the test, that kind of equation. You've seen it in your calculus test. All right, I'll sketch this graph up, and when we get back from recess, we'll go through this question, and then it'll be up to you how we dedicate our time. Okay, last one. Consider the function shown below with roots a, b, c, turning points at d and e, stationary inflection at f, and non-stationary inflection at g and h. Plot these points on the function alongside. So roots at a, b, c. So roots are where it crosses the x-axis. Those are the x-intercepts. All right, we have turning points at d and e. Now, turning point is when the function turns, all right, from increasing to decreasing or decreasing to increasing. So that's going to be here and here. Those are the local maximum and local minimums. And that's brought out in our table in 3C. So that is D and E. Okay, then we have stationary inflection at F. So we should recognise that's what's going on here. It's decreasing and then decreasing. So that's stationary inflection. And then non-stationary inflection at G and H. Okay, now those stationary inflection, hopefully we're okay with that. It's a stationary point. It's not a maximum or minimum, so stationary inflection. And then between any two stationary points will be a point of inflection. So we have a point of inflection there, and between these two, point of inflection there. Very good.
Does it matter if it's slow?
Nah, if it's like up a little bit or down a little bit. No, that's absolutely, yours will be up a little bit, won't you? Because I've probably exaggerated that feature a little bit. So yeah, as long as it's in the approximate position. Determine the intervals where the function is increasing. So what we're going to say is, when does this function have positive slope? So we can see it's increasing until we get to D. So for values of x less than D, and then increasing for values larger than D. Alright, now historically in the test we've done stuff like we've had point A has an x coordinate A, so we might say, for example, if you're speaking specifically about the x coordinates, you would use lowercase. That's a point, whereas this is a coordinate. It's a technicality, but just just so we're on the same page there, that's what's going on. All right, determine intervals when function's increasing. Oh, it just says increasing. Yeah, good, done. Part C, when is the slope decreasing at the greatest rate? When is the slope decreasing at the greatest rate? Now, points of inflection are when the slope is maximized. Now, not here because that's a stationary point of inflection, but it's occurring here and here. And so all we have to go is which one's going to be steeper? Is it going to be that point that's steeper or this one steeper? Just looking at the graph, we would say that H is steeper with G probably the second steepest point of inflection. All right, so it just has a steeper slope. We can tell just by doing a tangent to there and a tangent to there, it's steeper at H. So part C, when is the slope decreasing at the greatest rate? At point H. Now, the feature we're drawing out is that points of inflection are the steepest points on a graph, and then we're just asking, well, which one's steeper out of those two? Okay, draw a possible graph of f dash of x. All right, so what we're going to do is draw the sign diagram for f dash of x first. So all we're doing for the sign diagram of f dash of x is going, when is it increasing till we get to D, then we're decreasing until we get to F, then we're decreasing until we get to E, and then we're increasing. So that's what its graph will look like. Now on the Cartesian plane, we've got like D here, we've got F here, and E here. So it's positive until we get to D, and then it's negative, and then it's doing this kind of thing. There we go. All right. The other thing to note about this graph of the first derivative is that points of inflection on the original function, so G and H, correspond with the turning points. So those are going to be at x is G, and that's going to be at x is H. All right. So points of inflection on fx correspond with turning points on f dash of x. We emphasize that a lot. Okay, let's move on to the last part. Draw a possible graph of the second derivative. So all we're going now is the points of inflection are going to appear on here. Points of inflection are at G, F, and H. And we can see it's concave down until we get to G, concave up until we get to F, concave down between F and H, and then concave up. And so then just drawing a graph with those features. G is here, and then we have F and H. It's below, above, below, above. Gorgeous. All right. Any questions about that one?